This is our fourth and final video over section 4.3, and in this section we won't be looking at binomial probabilities. Instead, we'll be looking at the mean and standard deviation of the binomial distribution. We've talked about finding means of random variables earlier in this chapter. It's what we call the expected value. It turns out that if you can verify that the variable is binomial, there's an even easier formula that you can use to find the mean, to find the expected value. There's also a fairly simple formula for standard deviation as well, and we'll talk about that too. Here are those formulas. The mean mu and the standard deviation sigma of the number of successes in a binomial probability experiment are given by the formulas mu equals n times p and sigma equals the square root of n times p times q, where n is the number of trials, p is the probability of success, and q is the probability of failure. So again, very basic formulas, not a whole lot to them. Notice that there's no summations like we have to do for expected value. There's a square root, as you would guess, for a standard deviation, but other than that, this formula is pretty straightforward. You do have to remember what Q is. We haven't talked about that in a while. Q is the probability of failure, and remember that the probability of failure is always 1 minus the probability of success. Because success and failure are complements, the value of Q will just be 1 minus P. I know this screen's kind of busy, so I've rewritten the formulas on another slide. Let's recap. The mean is the number of trials times the probability of success. The standard deviation is the square root of the product of the number of trials, the probability of success, and the probability of failure. As long as you verify that the variable is binomial, you can use these two formulas. Let's do some examples. This first example will show you the links I'm willing to go to get you guys some real-world examples, because I read part of the British Poultry Science Journal, and just to make it clear, that's not part of my regular reading regimen. I did this for you. Anyway, in the Journal of British Poultry Science, they assume a 5% breakage rate for a particular method for packing eggs. This method was described in the paper. I didn't go into great detail, but it's a good method for packing eggs because you only wind up with 5% breakage. Suppose a random sample of 960 eggs is taken. Let's find the mean of the random variable number of broken eggs. Now, before we get into this being binomial and the formulas, let me just reword the charge of this problem, and I bet you'll have an idea how to answer it. Suppose I had said find the expected number of broken eggs. Remember that the mean of a random variable is just its expected value. So how many broken eggs would you expect to find? Well, if there are 960 eggs, and we assume a 5% breakage rate, I guess we would expect 5% of the 960 to be broken. So we would take 960 times 0.05 and get our estimate for the number of broken eggs. Let's see if that idea matches what the formula tells us to do. First, let's verify that this is a binomial experiment. We've got a fixed number of trials. We're going to test 960 eggs. And in each trial there are two possibilities. Either the egg is broken or it's not broken. So this is binomial. We're going to consider a success a broken egg because that's what we're counting up. The formula says that the mean of this binomial random variable is equal to n times p. We don't have to make a list of all of the possible outcomes and their corresponding probabilities like we did at the beginning of the chapter because this is binomial. We get to use this wonderful shortcut. So the mean is n times p. N is the number of trials, which is 960. P is the probability of success, and again, we're considering a success to be a broken egg, and there's a 5% chance that any egg will break. And this is the exact same calculation that our intuition told us we would be doing. 5% of 960 would be 48, and that's 48 broken eggs. Two different ways to interpret this answer. This says that the expected number of broken eggs in batches of 960 is 48. Or another way to interpret this is if we were to look at all possible random samples of 960 eggs packed in this way, the mean number of broken eggs amongst all such samples would be 48. Two different ways to think of it. That one's very intuitive. It's also easy to use. The standard deviation formula is also easy to use, but it's not nearly as easy to guess at. That formula is a little more complicated, and quite honestly, standard deviation is harder to understand than means. But once you've identified that the formula is appropriate, using the formula isn't hard. Let's look at that same scenario. and find the standard deviation of the random variable number of broken eggs. We've already verified that this is binomial, so we get to use the formula for binomial random variables. The standard deviation is the square root of n times p times q. We've identified n to be 960, and we've identified p to be 0.05. Q is the probability of failure, and the probability of failure is always 1 minus the probability of success. So Q is equal to 1 minus 0.05, which is 0.95. I hope that makes sense, because if 5% of the eggs are broken, then 95% of the eggs are not broken, and an egg that isn't broken would be a failure, because we're counting broken eggs. So 0.95. Now, taking 5% of 960 mentally was easy, because you can just take 10% of 960 and then divide by 2. This calculation I can't do in my head, so I'm going to go to the calculator with this. To type a square root, you push second and the x squared key. I have the older operating system running here, so I get the radical followed by a parenthesis. We're just going to type everything underneath the radical inside the parentheses. For those of you with the newer operating system, you'll get a radical that extends as you type, and you just want to make sure that all three numbers are multiplied underneath the radical. 960 trials times a 5% probability of success times a 95% probability of failure. You don't have to close the parentheses, but you know I'm going to. And we get a standard deviation of around 6.75. This is again measured in broken eggs. Now again, standard deviation isn't as easy to interpret as a mean. Means, averages, those are something that we're very comfortable with. Standard deviations are often used in comparison or in conjunction with other things. So just to get a feel for how we might interpret this, let's round this up to 7. 2 standard deviations would be about 14 eggs then. And remember that we said in Unit 1 that there's very little data that falls more than 2 standard deviations away from the mean. So anything more than 2 standard deviations away from the mean would be unusual. The mean is 48. If we add 14 to that, that's 62. So if we got a shipment of 960 eggs that were packed using this method, and there were way more than 62 broken eggs, that would be pretty unusual, and we'd have a reason to suspect that the breakage rate was due to something other than this method. That's the kind of interpretive stuff you can do with the standard deviation. To be clear, I'm not going to ask you to do that in this unit. We're actually going to do that kind of stuff in the next unit. But unless I bore you with that kind of stuff, there will be no reason for me to even bring up the standard deviation now. Let's look at another example. I've got a sports example here. From 2009 to 2019, NFL teams attempted to pass the ball on 58.5% of all plays, ignoring kicking situations. So just when a team was deciding between run or pass, they passed the ball 58.5% of the time. Suppose we analyze random plays from this time period in batches of 150, again ignoring kicks, just looking at when teams ran or passed. The charge of this problem is to find the mean and standard deviation of the random variable number of attempted passes. Now I chose a sample size of 150 because that's about how many plays would be run in a game, ignoring kicks. Finding the mean and standard deviation using the formula from earlier in the course would be quite arduous because we'd have to look at a bunch of different scenarios. But if we can verify that this is binomial, then we have these new simple formulas. So is this a binomial random variable? Well, we have a fixed number of trials. We're going to look at 150 plays. And there are 2 possibilities for each play. They either passed the ball or they didn't pass the ball. Even if I had included kicking situations in this analysis, we still could have said they either passed the ball or didn't pass the ball. It would still be binomial. But I thought it would be more interesting to look at situations that weren't obvious kicking situations, just deciding on whether to pass or run. So I took out the kicking situation. If you're not that interested in football, I apologize that I'm rambling about this. If I knew more about eggs, I would have rambled about that too. Anyway, this is binomial, so we can use our formulas. We know that the mean is equal to n times p, and the standard deviation is the square root of n times p times q. Let me copy those onto another slide since I didn't give myself much room here. The mean is equal to n times p. The standard deviation is equal to the square root of n times p times q. Let's start with the mean. We've got 150 plays. And the probability of success would be 0.585 because we're looking for pass plays. If they pass on 58.5% of all plays, then the probability of randomly selecting a play on which they pass would also be 58.5%. So n is 150, p is 0.585. So I'm going to take 150 times 0.585, and I get 87.75. You do not want to round this. I know there's a temptation to, because you might say, well, you can't have a fractional number of pass plays, but this is an average. It doesn't matter. It wouldn't be wrong to round it, but it's not necessary to round it just because it didn't come up to a whole number. I am going to put the label on here. This is pass plays. Again, I think that formula is very intuitive because you're just taking 58.5% of 150. The standard deviation isn't hard to do. It's a little harder to understand. We're going to take the square root of n times p times q. So n is 150, p is 0.585, q is 1 minus p. We're going to do 1 minus 0.585 to get the percentage of non-pass plays, or what would be running plays, because we're ignoring the kicking plays. So that's 0.415. Let's get this from the calculator. Got the square root of 150 times 0.585. If you're astute, you'll notice we already know that number. It's 87.75, so you could save yourself that trouble if you wanted to. But you need to multiply that by the probability of failure either way, which is 0.415. Enter. It comes out really close to 6. I'm going to put 6.03, but I couldn't fault you for just rounding it to 6. 6.03. Again, this is pass plays. So two standard deviations would be about 12. So adding 12 to the mean would be about 100. It would be pretty rare to get more than 100 pass plays. You could also take that standard deviation the other way. You could subtract 12 plays. So it would also be rare to get fewer than, say, 88 minus 12. Again, I know I'm digging deeper with that kind of analysis, but without that, that standard deviation doesn't mean a whole lot to me, and I assume you're in the same boat. Standard deviation on its own gives us the spread of the data, but so what does that mean? What do we do with that? Well, we can use it to determine what's usual and unusual. One more example. An exam of 20 problems consists of all true-false questions. A disinterested student guesses on all 20 questions. Find the mean and standard deviation of the random variable number of correct guesses. So we've got this student who doesn't care. Maybe they just flip a coin, and when it comes up heads, they put true. When it comes up tails, they put false, or they have some way of just guessing on all of them. If they're truly just guessing, then they've got a 50-50 shot at getting the question right. So we have a known probability of how often they'll get the questions right. This is a binomial random variable because we have a fixed number of trials. The exam has 20 problems on it. And in each case, you have one of two possibilities. Either the student guesses right or the student guesses wrong. As an aside, the most terrifying exam I ever took in my life was 20 true-false questions. I had a math test in grad school that was 20 true-false questions. And I was never so scared to get an exam in my life. You know, I'm a math guy, so I'm used to doing problems and showing my work and maybe getting partial credit if I have an idea that's slightly wrong. There was none of that on this true-false test. It was either right or wrong. I wasn't about to just flip a coin, though. But let's suppose that one of my classmates got the test and was like, well, forget this, I'm not wasting my time on this, and just guessed on all 20. Let's find the mean and standard deviation for all students who would do that. So we've already verified this is binomial. The mean is n times p, and the standard deviation we've used enough times now is the square root of n times p times q. N is 20 because there are 20 questions. P is the probability of success, and we're counting up correct guesses because there's a 50-50 shot of getting a true-false question right when you guess. The probability of success and the probability of failure are both 0.5. So not surprisingly, the average number of correct guesses would be 10. That'd be the expected value. Again, I think that's intuitive. If you've got a 50-50 shot at 20 questions, then your expectation is that you get 10 right and 10 wrong. It doesn't guarantee you'd get 10 right or 10 wrong, and that's where the standard deviation comes in. The standard deviation kind of lets you know what would be weird, what would be uncommon. So the standard deviation would be the square root of n times p times q. Q would be 0.5 because p is 0.5. If you got a 50% chance of getting it right, then you got a 50% chance of getting it wrong. This comes out to the square root of 5, and the square root of 5 is around 2.2 something. I'm not really sure. Let me put it in the calculator. Square root of 20 times 0.5 times 0.5, 2.24 if I round to the nearest hundredth. Two of those would be like 4, 4.5. So getting more than 14 correct guesses would be pretty uncommon. Getting fewer than 6 correct guesses would be pretty uncommon. That's our last example. If you have any questions about finding the mean or standard deviation of a binomial random variable, just let me know.